Ladies and gentlemen, it's my honor to make the oral presentation about our recent work during CGI 2020. Today, we are here to give a presentation on 3D hand mesh reconstruction from a monocular RGB image. Authors of this paper are Peng, Chuhua, Xian, and Yunbo, Zhang. Peng and Chuhua Xian are from School of Computer Science and Engineering, South China University of Technology. Yunbo Zhang is from Department of Industrial and Systems Engineering, Rochester Institute of Technology. My name is Peng, and I'm the presenter, and Chuhua Xian is the corresponding author. Okay, this page shows the main work we try to solve or improve our paper. Given a monocular RGB image containing a hand, in most cases, hand shape occupies only a small region in the captured image. If we directly conduct the training on the whole image, it will be no convergency because of the noises of the background. Thus, the first thing we need to do is localize and crop the hand area. Based on the cropped hand ROI region of interest, our model generates the binary mask of hand in the ROI, which will help the next part of our model to better understand and extract the information from such an ROI. Then the hand mesh can be reconstructed from the previous outputs by a Xian-based network. Finally, we can train a simple 3D hand pose regressor to get the 3D hand pose from the estimated hand mesh. Most of the existing method of 3D hand analysis based on RGB images mainly focus on estimating hand key points or poses, which cannot capture geometry details of the 3D hand shape. In this work, we propose a novel method to reconstruct a 3D hand mesh from a single monocular RGB image. Different from the current parameter-based or pose-based methods, our proposed method directly estimates the 3D hand mesh based on graph convolutional network. Our network consists of the three models, the hand localization and the mask generation module, and 3D hand mesh reconstruction module. The first module, which is a VGG16-based network, is applied to localize the hand region in the input image and generate the binary mask of the hand. The second module takes the high-order features from the first and use a Xian-based network to estimate the coordinates of each vertex of the hand mesh and reconstruct the 3D hand shape. To achieve better accuracy, a novel loss based on the differential properties of the discrete mesh is proposed. We also use professional software to create a large synthetic dataset that contains both ground truth 3D hand meshes and poses for training. To handle the real-world data, we use cyclogram network to transform the data domain to the real-world images to that of our synthesis dataset. We demonstrated that our method can produce accurate 3D hand mesh and achieve an efficient performance for real-time applications. This is the overview of our framework. These are 4 examples of our hand mesh dataset. Each row represents a sample, and each column indicates the type of data for each sample. Our dataset totally consists of 5 kinds of data. For example, the first column is RGB image. It's the input image, and the second is hand mask, indicates which pixels are hands. And the third is depth map. The fourth is hand mesh, and the fifth are hand joints data. In our dataset, there are totally 26,298 RGB images of the hand mesh from different eccentric perspective views. Now I'm going to introduce the hand localization and hand mask generation module. This module is composed of a backbone network and two heads. The VGG16 convolved backbone network takes a RGB image as input to conduct lantern features, which can be used by bounding box head to estimate the bounding box of hand. The bounding box is denoted as capital B. With the bounding box and features from stage 3 of VGG16, the task of Handmaster head is to generate the binary handmask of such an hand ROI. Yeah. This page shows the loss for hand localization and mask generation. For the hand localization and mask generation module, we define the loss of hand. We define the loss is equal to the bounding box loss plus mask loss. The bounding box loss equals to smooth L1 loss between the predicted bounding box and the ground truth. We define the hand mask loss critical L mask as the average binary cross entropy of all pixels. Thus, it's a pixel level classification problem. The second module is hand mesh reconstruction module. And the feature extraction backbone of hand mesh reconstruction module is a ResNet 15 based network which takes the concatenation of ROI hand image and binary hand mask as input to extract high order lantern features. Next, the lantern features is utilized by a course to find GCM to reconstruct the hand mesh corresponding to the raw input image. Note that before output the final hand mesh, our model produced two intermediate cross hand mesh. This page shows the loss function for hand mesh reconstruction. We define our hand mesh reconstruction loss as the weighted summation of vertex loss, edge loss, normal loss, and rotation invariant loss, respective. And in our implementation, we set the coefficients equals to 1. The first term of the vertex loss is the summation of square of Euclidean distance of the ground truth vertex and the estimations on the first intermediate mesh. The second term and the last term is derived from the second intermediate hand mesh and the last hand mesh respectively. The edge loss is about the length error of each edge between the estimated hand mesh and the ground truth. The normal loss forces the normal of each triangle on the estimated mesh to be the same as the ground truth. The last part of the loss is rotation invariant loss. Rotation invariant loss is based on the local frames of vertex on the mesh. We defined M sub I is the normal of vertex V sub I. E tilde sub I1 is the normalized vector of the projection of one edge ejecting from V sub I, and the local frame of V sub I is a triple. And triple is E tilde sub I1, E tilde sub I2, and N sub I, forming a right-hand side orthogonal basis. The definition enables intuition of the normal and tangential components at vertex I. And then the rotation invariant matrix critical T sub ij on the edge ij is encoded as like this. To maintain this matrix in training, we define the rotation invariant loss L critical L sub R as the summation of square of second order normal of the difference estimated rotation invariant matrix minus ground truth for each edge. This part are some are our experiments. This is the implementation. We implement our method using Keras framework with TensorFlow. We firstly train the first module and then fix the parameters in the first module and train the whole network for 70 approaches. We train and test our method on our synthesis dataset, and we use 21,038 for training and 5,260 for test. The images are resized to resolution of 512 times 512 with 12 pixels, 0 padding at the right and the bottom size. The runtime of model outputting is 23 microseconds. Thus, our including 12 microseconds of hand localization and the mask generation model, and 11 microseconds for 3D hand mesh reconstruction model. Thus, our method can meet the real-time requirement on GPU at over 40 frames per second. Firstly, we conducted ablation study of loss terms. The column name of this table indicates which loss term is excluded during the training procedure. Clearly, the model trained with full loss produced the best result. We also studied the impact of intermediate mesh supervision and feature recognition step of the hand mesh reconstruction model. And we compare our loss term to the loss function proposed in Ge et al. This table demonstrated that our loss function performs better than the intermediate mesh supervision, and the feature recognition step has a positive impact on the final loss. And our loss function is better than the one proposed in Ge et al. This page shows some comparative examples about the loss function between ours and Ge et al. Clearly, the model trained by our loss is able to reconstruct better 3D hand mesh, and our rotation human loss term can preserve the shapes of hand better, undergoing large rotations of hand fingers. Moreover, we compare our mesh reconstruction method with the direct linear blend scaling method. To conduct the LBS method, it requires to estimate hand key points from the input images. In this experiment, we used the methods in Merner et al. And Zhang and B et al. To train the networks to directly regress 3D hand key points on our synthetic dataset. And then we apply the direct LBS to reconstruct the 3D hand mesh with the predefined hand mesh and scaling ways. The table and picture results show that our method achieved the best performance. The 3D hand mesh reconstructed by our method are with higher precision and are more full and natural. We also implement our hand shape reconstruction method on no object subset of freehand dataset. And these are some results illustrated the performance of our method validated on the selected subset of freehand dataset. After reconstructing the 3D hand mesh from the input image, a 3D hand pose can be estimated by a 3D hand pose regressor. This framework of our simple 3D hand pose regressor, this is the framework, take vertices matrix as input and output the target pose vertex matrix. We use the time distributed layers in Keras to wrap our MLP model. The figures shows the comparisons with two state-of-art methods on our synthetic dataset. The area under the curve values are shown in the parentheses. Our method achieved the highest AUC values. The value. Actually, if the trained model on our synthetic dataset is directly applied to real-world images, it will induce unacceptable results because the limited generalization of the trained model. Since there is no annotated dataset of 3D hand meshes with real-world RGB images yet, we utilize the cycle gain network to conduct transformation of the data domain in this work as illustrated in this figure. We use the cycle gain to transform real hand images from the original domain to the one corresponding to the generated handmade images, which can significantly improve the performance of our model, which trained on our synthetic dataset when validated on the real-world images. Here we show some reconstructed examples with and without domain transformation. Clearly, image domain transformation makes great contribution to the reconstruct precisely 3D hand mesh from real-world images. This figure shows 5 examples of our test about robustness of occlusion and incompletion. From this figure, we can see that our reconstruction network can produce fairly good results even the input images does not capture a full hand. It should be pointed out that there is no such annotated data with incomplete images used in our training data, and this demonstrates our method can handle the cases of serious occlusion or incomplete hand images well. Actually, our method cannot directly reconstruct the hand shape from the real-world image yet, and it requires a data domain transformation. In our future work, we will try to develop an efficient method to directly reconstruct 3D hand mesh from real-world data without data domain transformation, and we will also increase the number of poses of hand in our dataset to increase its generalization in the future. Thank you.